Welcome back all of you. In the last two classes, or even three classes I would say, we discussed a lot about multi-dimensional NMR, focusing mainly on two-dimensional techniques, and explained to you the time dependence, choosing the dimensionality, what is the advantage of different two-dimensional experiment, what type of experiment you have to choose, and what is the polarization transfer mechanism for some of the pulse sequence like inept, toxy, rosy, etc. A number of pulse sequences which are commonly used, both homonuclear and heteronuclear, were discussed. I took the special example of a COSY, which is a simple two-pulse sequence where I discussed and explained how the magnetization between two coupled spins, especially when I took the example of A and X, how it gets transferred from A to X or X to A. I said in the evolution period T1, the precision frequency of spin A, when it remains same in detection period also, it gives us a cross peak. It gives us a diagonal peak, which frequency remains same, nu A and nu A both in T1 and T2 dimensions. However, it gives it magnetization to the coupled spin also. As a consequence, then in the frequency domain spectrum, you are going to get a peak which is different. In addition to diagonal, you may also get a peak in the frequency domain spectrum, that is a cross peak. This is what we discussed, and I took an example and showed how we get the cross peaks and how we get diagonal peaks. So please remember, diagonal peaks in the COSY come when there is no coupling. As a consequence, if there are n protons, let us say, none of them are coupled among themselves, in which case you get only peaks on the diagonal and nothing else. And what do you get in the one-dimensional spectrum? Exactly same. As a consequence, the diagonal spectrum of the COSY corresponds to one-dimensional spectrum. Simple. Please remember that diagonal peaks in the COSY spectrum corresponds to simple one-dimensional spectrum. Now let us take some example of a 2D COSY spectrum of uncoupled spins. Two uncoupled spins I am taking. Let us say one is precessing at frequency nu A, other is precessing at the frequency nu X. Now when we take the COSY spectrum of this molecule, we are going to get spectrum like this. Remember, I said these two spins are uncoupled. As a consequence, this nu A has the same positional frequency both in T1 dimension and in T2 dimension. Similarly, the spin nu X has the same frequency both in T1 and T2 dimensions. So then what is the type of peak you are going to get? You see, you are going to get peaks only on the diagonals. And because there is no J coupling, remember as I said in the last class, J coupling is one of the requisite for the COSY. Only then the polarization transfer takes place between two coupled spins. That is a mechanism of transfer through J coupling. Now J coupling is not there. So this continues to precess and it will not transfer its magnetization to nu X in the T1 period. Similarly, nu X will not transfer magnetization to nu A. So there is no cross peak at all. What we are seeing is only diagonal peaks. So this is the 2D plot, 2D spectrum in the contour part. Okay, contour. Now we can do one more thing. We can get the spectra. This is the diagonal, contains only the chemical sheet information. Now I can plot the projection of the spectrum. This is the F2 projection. The spectrum, if I take the projection and plot on the top of it, this peak comes like here, this peak comes here. This looks like a one-dimensional plot. Of course, it's not one-dimensional spectrum. Plot looks like one dimension, not correspond to this diagram, one-dimensional spectrum, and it is a projection. Of course, if there are peaks here, that will also come. Okay. Now, you can see, take the same projection along this side also. I'm sorry, this should be F1 projection. There's a typo. It has to be F1 projection. The projection along this axis is F2 projection. This is the way normally 2D COSY spectrum is plotted. You get the spectrum plotted in both the dimensions, both the frequency dimensions, and you can start looking at the peaks. These are the diagonal peaks. If there is a coupling, if the spin gives its magnetization to a coupled spin, you get cross peaks which are symmetric with respect to the diagonal on either side. Because remember why it is symmetric. Nu A gives peak to nu X. Nu X also simultaneously gives peak to nu X. So with respect to the diagonal, because chemical shift range is both same in both the dimensions, the cross peaks in the COSY is always symmetric. Okay, this is the spectrum corresponding to two uncoupled spins. Okay, now let us consider the example of what type of information COSY gives. The presence of scalar coupling interaction between the spins is the basic requirement I said. If I take a molecule like this and start looking at the 2D COSY spectrum, what I am going to get? This is coupled to this through J coupling, and this chemical shift of this comes at the diagonal, chemical shift of this comes at the diagonal, and because there is a J coupling, and these two also give rise to cross peaks. Similarly, this and this gives us a cross peak, and this give us a cross peak. It can go like this. It can go on and on like this. So what I'm trying to say is, so long as there is a coupling, you get cross peaks to all the coupled spins. Of course, depending upon the mixing time and the strength of coupling, you may also get long range coupling in COSY. You can see this is coupled to this also. You may see this coupling, this cross peak also. It doesn't give energy. See this, let us say this proton in the T1 period, it is persisting at certain frequency and gives part of its magnetization to this. You can also give part of the magnetization to this because it is coupled if there is a long range coupling. It is not restricted only to immediate neighbors. Of course, probability of this is immediate neighbors because that coupling strength is larger. But does not mean it cannot give its magnetization to the protons which it is coupled to, which is 2 or 3 bonds away. It can also give rise to long range coupling and a cross peak to that one. So this is the thing. So although I have written 2D COSY conventionally identifies immediate coupled neighbors, please remember you can also get cross peaks to the long range coupled protons. Please remember this point. Okay. Now I'll take the COSY pattern of two spins which are weakly coupled. Coupled. In the previous example, I took uncoupled. Now what is the pattern you are going to get if the two spins are coupled? And if the two spins are coupled, already we discussed, and especially weakly coupled case, it must be treated like two AX spins. So we will get doublet for A and doublet for X. This we have already analyzed n number of times, so I don't have to repeat it. So let us say this is the AX spectrum. I am going to plot the projection. The projection is nothing but what you see on the diagonal here. This is the F2 projection. This is the F1 projection. And I call this as chemical shift of A. This is chemical shift of X. Same spectrum I am getting in this dimension also. Because I am correlating only chemical shifts. Identical spectra I am getting in both the dimensions. Okay. This is the diagonal. Now, in the COSY spectrum, what are the peaks we are going to get? First, identify the dimensions. This is F1 and F2, T1 and T2, omega R, omega 1, omega 2, whatever you want, you can identify. Now, first I am going to get identify peaks on the diagonal. See, I am going to identify 1, 2, 3 and 4. 4 peaks are on the diagonal corresponding to chemical shifts or frequencies of 2 doublets for all the 4 peaks. There are certain peaks here and here. We will see that. We'll come to that later. And what does it mean? The delta A is precessing in both T1 and T2 dimension with the same frequency. So it gives rise to the peak at its own frequency. That is diagonal peak. So this is nothing but nu A comma nu A. In the F1 dimensions also, F1 dimension is this frequency is nu A. If you come in the F2 dimensions also, this frequency is nu A. So it appears at its own frequency. This is a diagonal peak. Now similarly X also appears at its own frequency because the frequency of X, the precessional frequency, remains same both in T1 and T2 dimensions. Fine. Now if you look at this, there are cross peaks between them. There are, see, these two are doublets, and we know this is coupled to this, and there is a polarization transfer between this pin and this pin. Okay. When it happens, when this pin gives a part of its magnetization to this in the T1 dimension during the evolution time, or this gives to this because of coupling, I said we get cross peaks. True. But why there are extra peaks here in addition to diagonal? These are also cross peaks. These are in both A and X, we get what is called autocorrelated peaks. They correlate within themselves. A spin, the doublet pattern, correlates within itself. It is not the correlation to another spin. The doublet pattern, 2P frequencies, will correlate within itself. That is called autocorrelated peaks. So you can see these autocorrelated peaks both for A and both for X. Both are autocorrelated peaks. Is it clear for you now? But remember, this does not tell me about which spin is coupled to which. This is simply within the multiplate, there is a correlation. That's all. Doesn't give me any additional information. Simply remember, this is an autocorrelated. These are autocorrelated peaks. A correlate within itself. X correlate within itself. Gives a frequency within itself. Okay. This is what I said. A appears at its own frequency. X appears at its own frequency. Both give autocorrelated peaks. Now, the frequency of A is modulated at the frequency of its coupled partner X. I told you. A gets modulated because of X, because it gives part of its polarization to X during evolution. Similarly, X gives part of its polarization to A. The frequency of A gets modulated at the frequency of its coupled partner. So what will happen? A is going to give cross peaks. So now at the frequency of A in the F1 dimension and at the frequency of X in the F2 dimension. Please understand. This is the frequency of X in the F2 dimension. This is the frequency of A in the F1 dimension. So because it gets modulated due to the frequency of coupled partner, A will give rise to frequency at X, at its coupled partner. Now what happens to X? X also gets modulated because interaction is mutual in NMR. So X also gets modulated at the frequency of A and gives rise to cross peak at its coupled partner A. Now you understand, A not only gives frequency at its own frequency, it gives rise to autocorrelated peaks because of the splitting pattern. Frequency of A gets modulated with the frequency of A because it's a coupled partner and gives rise to frequency cross peaks or peaks at X. Similarly, X appears at its own frequency. Not only that, it gives rise to autocorrelated peaks for its splitting, for its doublets. In addition to that, X gets modulated because of A. These two interactions are mutual and gives us the cross peak at A. That's what it is. So when the frequency of A gets modulated with the X, you got here. X frequency gets modulated, you got cross peak here. Simple logic. If there are three protons are coupled among themselves, then if at the frequency of A, M and X get modulated. Let us say I have three spin protons, A, M and X. At frequency of A, M and X also get modulated. So you get cross peaks at M and cross peak at X. If you look at M gets modulated at due to the frequency of A and X. So it gives cross peaks at M, A and cross peak at M. Similarly, X has a coupled partner A and M, and it modulates the frequency at A and M, gives us the cross peak at them. So this is simple logic. Whenever the coupled spins have the frequency modulated at the respective coupled partner, there you are going to see the cross peaks. Please understand. So whenever this coupled spin gets modulated with its when one of the spin gets modulated its frequency with its coupled partner, at that frequency you get a cross peak. So this is what happens. So you got cross peak. So these are called cross peaks. Okay. Now, not generally, always remember, in homonuclear 2D COSY, the cross peaks must appear as pairs, symmetric with respect to diagonal. Cross peak always appears as pairs. Remember, you saw it, behind. This and this always appear as pair. If A gives cross peak to X, X also has to give cross peak at A, and it is symmetric with respect to diagonal. You see, it has to be perfectly symmetric. This is one of the pattern for COSY. Please remember that it has to be symmetric with respect to diagonal. So now with this, what we will do is, let us see. I have a mixture of two AX spin systems. I have chosen this molecule deliberately. This and this gives rise to coupling. It forms a coupled spin system. I assume chemical shift between these two protons are sufficiently large compared to scalar coupling. So I consider this as weakly coupled spin system AX. I chose another molecule. Similarly, I will say these two protons also form weakly coupled AX spin system. Now I take the mixture of both the molecules and want to do the COSY. How does the 1D NMR spectrum look? First of all, this looks like this. Why? Each AX spin system gives us to 4 lines. 2 lines at A and 2 lines at X. This we have been discussing for quite some time. So there are 2 such AX spin systems. So you should get 8 lines. And what are these? One is a chemical shift of 1, 2, and 3, and 4. All the 4 protons are there. I have 4 chemical shifts. And each of them is a doublet because each one is coupled to its coupled partner. So because of that, there are two sets of 2 doublets. Now the question for me is, what are the coupled partners? I don't know. I have just taken the 1D spectrum. This is what I get. Now, I want to know in this spin system, where I want to identify which are these 2 doublets and which are these 2 doublets. Now, if I am asked a question, whether this and this form a pair of doublets, whether these 2 form pair of a doublet, whether this and this form pair of doublet, or this and this form pair of doublet, I do not know. There are several possibilities here. I am getting a conventional spectrum. Now I want to identify the coupled partner. Let us say 2 reds are coupled partners and 2 blues are coupled partners. Then I know this is chemical shifts of A and these are all chemical shifts of A and X, A and X. Fine. What about now coupled partners are 1, 2, and 3, 4. What about 1, 3, and 3, 4? You do not know. These 2 could be coupled partners, 1, 3, and 2, 4. Also, these 2 could be coupled partners, 1, 4, and 2, 3. So various possibilities are there. Now if we are asked to find out which are the coupled partners, what you will do? Simply run a COSY experiment. Now, what is the type of pattern I am going to do? For a COSY experiment, tells me which are the coupled partners. Please understand. Simply do a 90 T190 COSY experiment. That's all I'll do. Two-dimensional COSY. Now, my first condition is possibly 1 and 2 are coupled partners. I don't know. Or 3 and 4 coupled partners. If this is the situation, what type of spectrum, COSY spectrum I get? Look at this. These are all diagonal peaks and autocorrelated peaks. Now, if these two are the coupled partners, 1, 2, now I'll get cross peaks at 1, 2. And if they act similarly, 3 and 4 coupled partners, I'll get. See what another interesting thing you should know is they are symmetric with respect to diagonal. To identify the cross peak, all what you have to do is sit at the center of this peak, doublet. Come vertically down. Come to the center of this doublet. Go horizontally. You meet the diagonal. Again go vertically up. Complete the square. You form a beautiful square because cross peaks in the COSY are symmetric with respect to diagonal. Then I know diagonal peak, if you see this and this, these two are the two protons which are coupled between them. So the cross peaks tells me there is a cross peak between this and this here and here. That means this proton and this proton are coupled. There is a J coupling between these two. So this is one of the AX coupled spin system. This is one of the coupled partners. Clear? Now, let us look at other one. So I completed the square. Started from the center, come down, went and completed the square. This undoubtedly tells me delta 1 and delta 2 are coupled. Go to the next one. You should get the pattern similarly for 3 and 4 because this is the chemical sheet of 3 and this is the chemical sheet of 3. Look at the spectrum, come down, go horizontally, go up, complete the square. So this diagonal peak and this diagonal peak are there, this proton and this proton are coupled. And that's why we're getting the cross peaks for these two. So delta 3 gives diagonal peak and also cross peak with its coupled partner 4 here. Similarly, 4 gives a diagonal peak and also gives cross peak with its partner here, delta 3. So they are symmetric. Perfect. Now I know what are the coupled partners. This was assuming these two are coupled partners. This should be the type of COSY spectrum you get. Now what happened to the second possibilities I thought? I thought this could be coupled partners, 2 red and blue, 2 blues are there. Maybe these 2 red doublets are coupled. These 2 blue doublets are coupled. They are coupled spins. We don't know. Now if that is the situation, how my 2D COSY spectrum comes? Again, write down the diagonal peaks. Now, because these two are coupled partners, the cross peak appears between 1 and 3. Perfect, you see? From the center of this delta 1, come vertically down, go horizontally up and complete the square. That shows delta 1 and delta 3, which are diagonal peaks, they are coupled. As a consequence, they give cross peaks between them. Clear? So if these two are coupled, delta 1 and delta 3, this is the cross peak pattern you should get in COSY. And if delta 2 and delta 4 are coupled, again, you get the cross peaks like this, between 2 and 4. Now, this is the pattern. Look at the pattern for this COSY spectrum when these two are coupled, and the COSY pattern we saw when these two are coupled. Entirely different, but it gives you fantastic information about coupled partners. You can find out which is coupled to which. Fine. Now, what is my last possibility I thought of? I thought of one possibility. 1 and 4 are coupled and 2 and 3 are coupled. Now tell me How do we get the cross-peak pattern? Again, write down the diagonal peaks. Now I am assuming 1 and 4 are coupled. 1 should give rise to cross-peak to 4. Should be here. Similarly, 4 should give rise to cross-peak to 1. It is here. So now start from here, come down, go horizontally, go up and complete the square. Now you identified these two coupled partners. Similarly, now go to 2 and 3. 2 and 3 give us the coupled partners like this. 2 gives cross-peak here, 3 gives cross-peak to 2, and you can complete the square. See the patterns, depending upon which proton is coupled, there are 3 possibilities, and we saw 3 types of coupling patterns. Cross-peak patterns are different in the COSY. So then you can identify easily coupled partners. This is a hypothetical example. I took 2 coupled spin system. I wrote a stick plot here to make you understand. But in reality, you can understand yourself. And let us try to now start with a simple example, a realistic example of a COSY spectrum like this. The 1D spectrum of this molecule is given as a projection here. Now, this is a CH3 proton. I know it always comes at high field. Of course, it's a simple spectrum I can interpret. Assuming I don't know anything about analysis, I simply ran a COSY. Now start with one peak. At least something we will have to start. We'll start with this peak. I know this peak is coupled to this because you start from the diagonal, come vertically down, go horizontally and complete the square. That shows that this peak, this diagonal peak corresponding to these 2 protons are coupled. I identify the coupled partner. That must be this CH3 and this CH2. Fine, because it's a triplet and a quadruplet. But you can see from your molecule, this CH2 can also experience coupling to this. That's why we have a pentate pattern. We know that, pentate or sextate pattern we are seeing. So we'll continue further. We identified 2 protons. Now, from the CH2, which you identified, continue further. And you can form another square. Come here, hit a cross peak, go horizontally and complete the square. You see another peak. So that means this proton and this proton are also coupled. And this proton corresponds to the CH2. That means this CH2 is coupled to this and also this. Very easy to assign. You understood now how to assign the COSY spectrum. And OH, there was no cross peak because OH is not coupled to. So I am not seeing any cross peak to OH, so it doesn't come. In principle, it should have been, there should have been a diagonal peak. It is missing. It's okay. So now let us look at this molecule, 2-chlorobutane. I know the formula, I know the spectrum. Of course, again you start the interpretation. Start with the one of the peak which you know. I think this must be CH3. We all agree, right? High field it is coming is a triplet because of the CH2. Let us start with the assumption. Start with that peak. Oh, we can start with this CH3 because it's a doublet because of this. That's also fine. We don't have to start with this. We can start with this also. So with that CH3, now come vertically down, go horizontally. Then you will hit upon, you will complete the square. You hit upon this proton. Then this must be CH because the CH3 was a doublet. CH3 was a doublet because it is coupled to CH. And the CH is a quartet because it is coupled to CH3. You identified that. Now what is next? You can also see that this CH, if you carefully see, has 2 cross peaks, one here. Okay. In addition to that, it has another cross peak. You trace this completely and you will see it is going to hit upon this diagonal peak. This is CH2. So this CH2 or this CH proton is coupled to the CH2. Is giving us a cross peak. Now this CH2 Again complete the square. This CH2 is coupled to this CH3. You see, you can complete the square. From this, go horizontally, vertically, complete the square. So very easy. In a systematically, stepwise manner, you can go. Started with the CH3, which I knew. I completed this one. I hit upon CH. I know that. And I also came to know this CH is coupled to CH2. From CH2, I can find out it is also coupled to CH3. So entire coupling network I could assign by one spectrum. That is the beauty of COSY. See, let us quickly go to another molecule, ethyl 2 butyrate. Now, there are 5 groups of chemically inequivalent protons, 1 and 2 here, 1, 2, 3 here, identified as A group and B group. Fine. Now, let us look at one of the peaks which you think is easily assignable. Let us look at this B. I just see a 3 proton here. It was named numbered 5. If you carefully see, it is a triplet. It is not expanded. If you see, it is a triplet. No doubt about it. We'll start with the known one. From CA3, come down. You hit upon a peak. Again, complete the square. And you see this peak. This form is a perfect square. That CA3, this CA3 is coupled to this one, that is CH2. And there is no other coupling possible, only one independent square. See, you cannot find any more coupling to either CH2 or CH3. No cross fix anywhere. Clear? That shows this form a coupled spin system. Then what is left next? Next, we consider this one. This could be this terminal CH3. Start with this, come down, and then complete a square. So A is coupled to 2. Fine. But at the same time, you see, A has one has two cross peaks. It also has a long range correlation to this proton. You understand? See, now 1 is coupled to 2, also to 3. And 2 is also coupled to 3. And 1 and 3 are coupled. You understand the point now very clearly? 1 is coupled to 2. That square is completed. At the same time, you see cross peak between these two. Then what is left over? This is 3. So this is a diagonal peak. There is a cross peak between this peak and this peak. So this must be proton 3. Also, you can see there is a cross peak between 3 and 1. You can see the cross peak here and here. So complete the square. Now you see the cross peak between 3 and 1. So 1 has a coupling to both 2 and 3. It formed one coupled spin system. Interestingly, we saw long range correlation in this COSY spectrum. And this is another COSY spectrum, another spin system where we got only correlation to 2 coupled partners. I hope you understood how we can interpret the COSY spectrum. Well, this is the last example I will take so that you become more familiar with the COSY. There is no point in continuing further like this. There are infinite number of molecules there. You can keep on interpreting, analyzing several till you become conversant. But I am giving you the idea, I am giving you the hint how to go ahead in analyzing the COSY spectrum. I think with this you can continue further. Now here, there are 7 groups of chemically inequivalent protons. This is a very famous molecule. You can see in most of the literature and in web you can see this type of spectrum, this molecule. Everybody takes this as a fantastic example to analyze the COSY, TOXY, etc. Now where do you start here? Remember, there are 2 CH3s here. They are coming here. Both could be attached to CH2 and CH2. They are, as a consequence, both are triplet. But I do not know which is which. But there is one clue for me. This CH3 is coupled to this CH2 and there is a break here because there is no proton here. This should have a long range coupling. If that coupling is not seen, this forms one spin system and this forms one spin system. So you must get cross peaks between these two and cross peak among all these coupled partners. That is one hint for me from looking at the molecule. So let me start like that. Start with the CH. Other way out is CH2 group closest to the ketonyl. That's correct. CH2 group closest. These two peaks should be shifted to the downfield because of CO. Either this or this. That's what we have to take. No problem. The CH2 group closest to ketonyl, ketone carbonyl, either this or this, both of them will come to downfield. And you can, I see it is written here, both are 2 and 4 written. Now, one of them you take, it will complete a square. And no other coupling you can see here. Carefully if you see, this will form a square. And this has to be 2 coupled to 1. It forms a set of coupled spins. 2 spins which are coupled, nothing else. No other coupling is possible. But if you go carefully, there is another one here. See, this is slightly different frequency. If you draw a line, this is like here. And this frequency is slightly above. This forms a line with this. Now another that completed. Now we'll start with next. If there is a confusion here, we start with the CA3 because this CA3 is identified. Now we come to CA3 here. Easy, because we cannot make a mistake with CA3. Once you know this CA3, this has to be proton 7. Start with that. Come down and complete the square. What do you understand? Proton 7 has a coupling partner with 6. It has to be 6. Clear? So you formed a square. But this is not the end. Continue. This diagonal, from this if you come down, you see one peak here, go horizontal, go up, and you see another peak here. There is a some error in this writing. Don't worry, these lines have shifted a bit, but this is cross peak. You can see now 6 is coupled to 5. It forms a cross peak. Now go down further. 5 is coupled to 4. That is also understood now. So very clearly, you could identify all the spins which are coupled in this group, all the spins sequentially you can say and find out this is coupled to this is coupled to this is coupled to this. You identified all the peaks and you identified this coupled spin system as a separate independent group. Everything is clear now. This is the way you can go ahead and analyze any COSY spectrum, however complex it is. Simply look at the diagonal peak, and then if you happen to see a cross peak, find out its diagonal, which is equidistant on either side, which is giving cross peak, and that must be the peak on the diagonal. These two are coupled. Like that, you can identify the coupled partners. So what I'm going to do is, I will stop today. In next class, we continue further and more about other 2D experiments.